Hi, good afternoon, everyone, and good morning also to those joining from the UK. So, Assalamualaikum warahmatullahi wabarakatuh. Welcome to the seminar guest lecture series on artificial intelligence and machine learning in healthcare, organized by the Department of Health Policy and Management at the University of Gadjah Mada in collaborations with the Indonesian Associations of Health Informatics, Aptirmiki, IPK, as well as the Center for Health Policy and Management. This guest lecture is actually also part of the massive online open course on AI in healthcare, designed to bring together global expertise and practical case studies to strengthen educations, research, as well as practice in these fields. My name is Lutfan Lazwarti, and I will serve as moderator to these sessions. So today our theme is AI for predictions and clinical decision support, a rapidly advancing area where AI is reshaping our future healthcare from disease prediction as well as to improve diagnosis and also for clinical management. And we are honored today to welcome two prominent speakers, Professor Yun Chung Chang, the Director of Graduate Institute of Data Science at Taipei Medical University, and also Professor Paul Taylor, the director of the UCL UKRI Center for Doctoral Training in AI-enabled Healthcare, University College London. So, well, today we'll have both of the speakers their presentation for 30 minutes each, and then we will have a chance to have a question and answer afterward. So, without further ado, I think we can start right now, and we'll kindly ask Professor Yun Chung Changs to deliver his lectures. And the title is The Future is Here. So unlocking the potential of clinical data with large language model. So Professor Changs, hopefully the sound is clear. And yeah, now your time to give the presentations.
Okay, can you hear me?
Yes, yes.
Okay, thank you for your introduction and invitation. Okay, let me share my slides. Okay, yeah. So can you see my slides?
Yeah.
Okay. All right. So yeah, firstly, I would like to thank you invite me to give the short talk, and yeah, it's my pleasure to be here to share my recent research work. So the title of this talk is "The Future is Here: Unlocking the Potential of Clinical Data with LLM." LLM is a large language model. Okay, my name is Yongchun Zhang. So this is about me. I am the professor in the Taipei Medical University Graduate Institute of Data Science, and also the director here. And my expertise is about natural language processing and the large language model, especially the clinical artificial intelligence. Okay, so if you interested about the talk, maybe you can browse the website, my lab website here. Okay, so actually there are many research topics in my lab. So as you can see here, many NLP research work. So if the data is related to the clinical, so we call it clinical NLP. Okay, so if the data is from social media, we call social NLP, also financial NLP. So we have lots of different NLP topic. Okay, and recent year we also do some medical image task. Okay, and also use AI technique in the sport technology. Okay, all right. So what is the text data in clinical environment? Actually, I would like to say the clinical report is a treasure because the report content the human readable content, okay, instead of the image, okay, and also conclude the diagnosis from the doctor. So there are many knowledge in the text data, clinical text data. Okay, so it's a treasure. Right. So if we want to do the natural language processing in the clinical research field, what challenge you will need to face. So let me show you some example. The first is the text data from the emergency department. Okay, as you can see here, there are many tokens here, and the language mix situation, as we can see. For example, in Taiwan, we sometimes use the Mandarin Chinese, and also the English. So as you can see, the text here is the mixed language. Okay, and also the content is very short. For example, when we post the Facebook or the Twitter, we only can post about 120 tokens. But as you can see here, the chief complement is shorter than the social media. So it is difficult to process it. All right. So another example is the radiology report. Okay. As you can see here, even we want to recognize whether the patient have the metastasis. If we use the keyword based, we cannot recognize it very well. Okay. Another example is the pathology report. So pathology report is longer than the case we show you before here. Oh, sorry. So it's a long text. So how to process the pathology report efficient is very important. Okay. So I show these three examples have different challenge in the clinical NLP. Okay. So what is the trend of the large language model? All right. As you can see here, the first trend is the model become larger and larger. But another trend here is become smaller and smaller. Okay, so we called small language model. Okay, so the right-hand side, you can see the Unicorn company also proposed their own the small language model. For example, Meta have the Llama 3, and the Microsoft have 5.3 or 5.4, and Google have another small language model called Gemma. Okay, so many unicorn companies start to develop their own small language model and release the small language model so everybody can use it for the applications. Okay, and in this slide, I wanted to point out the language model is very smart. For example, the average IQ of human is 100. As you can see in this figure, many large language model is performed well, more than 100. Okay, so that means the LLM is very smart. Okay, and also I need to mention a platform called Hugging Face. So there are many state-of-the-art models. If you survey the paper, and maybe the paper can provide you a hyperlink that can connect to the Hugging Face. So that means you can download the state-of-the-art model from the Hugging Face, and then you can run the model on your laptop or the GPU environment. So it's the right time that we can use the large language model to for our application, clinical applications. Okay, so what is the real world NLP application we need to face the challenge? So maybe the text data is from the image or the PDF file. So firstly, we need to use the OCR toolkit to convert the text from the image. Okay, and then we have a raw text data, and then the raw text data is the NLP task, or maybe the data came from the voice. Okay, so we need to use the speech recognition model to recognize the content of the voice, and then it's a NLP task. Okay, so the challenge of the challenge and the difficulty of the clinical NLP there are many issues about it. So firstly is the data governance. So how to collect the data from the clinical environment is very important issue, and how to share the data to our cooperated safely also is very important issue. So another issue is about the mixed language. So as I show you before, the example about the emergency department. So the language is mixed. So in Taiwan, we have the Mandarin Chinese and the English text. So another issue is the small data, not big data. So I believe you guys know in the clinical environment, we collect the data or the data from the patient. So eventually the data is small data, not big data. Okay. So another issue is about the cost of the data annotation, because only a doctor or nurse can help us to annotate the data. So without the annotation, we cannot train the model. All right. The last two issues is about the data imbalance and the model explanation. Okay, so those 6 issues for me, it's very important and a challenge in the clinical NLP. So here I will share 3 research work. The first is the lung cancer treatment. So how to use the NLP for the lung cancer treatment. Okay, so in this research, we focus on the late stage lung cancer treatment. Okay, because it's a late stage, so we can provide the drug or the treatment, and there is a very important issue is about the clinical trial matching. All right, so the right hand side, I list 4 tasks. Maybe the NLP technique can deal with it. The first is the report generation. Okay, I need to point out this research is start on 2020, because from after 2022, large language model can generate clinical report very well. All right, so I will introduce how we developed a model to deal with this problem. All right, so the second task is about the diagnosis. Okay, so we want to use the natural language model to summarize the pathology report. Okay, so we call the summary generation. And the last is about the treatment. So we want to use the NLP technique for the drug selection and the clinical trial matching. All right, so first is use the NLP technique to generate the radiology report. So the input data is the CT scan. Okay, it's a image sequence. All right, so there are about 200 image will generate after CT scan. Okay, sorry. So as you can see here, there is a computer vision model. So given an image, the computer vision model can recognize the nodule, and then extract the feature from the image, feed into the second model. The second model is NLP model. So what task does the NLP model do? So the model firstly will predict the semantic of the image. For example, what is the texture of the nodule, or what's the size, and the malignant probability. Okay, and then the last step is to generate the report. All right. So here we use the template-based approach to generate the report. Okay, so as you can see here, the generated report for the image, there is a 8.4 mm solid nodule. All right, and based on the long rate version 1.1, the score is 4A, and the malignant probability is about 100. So it's very high. All right. And the last point is suggest closely the follow-up and the food biopsy. Okay. The second case, as we can see, it is not serious than the first. So it's a pure GGO nodule, and the score is 2. Okay, so the malignant probability is lower than the first case. Okay, so we can generate the prototype of the report. Okay, so from 2023, the report is very similar to the prompt of the large language model. So we use the model called Vacuna to generate the report. Okay, so the input is the prompt from the our previous work and fit into the Vacuna model, and you can see the report is better than previous. Okay, all right. So these slides, I want to play a short video to introduce the second and third and fourth task I mentioned for the NLP for lung cancer treatment.
Taipei Medical University employs generative deep learning for the prediction of late-stage lung cancer drug efficacy and prognosis, along with the screening of global clinical trials. Among the top cancers in Taiwan, lung cancer is the leading cause of death, with 70% of patients already in the terminal stage when diagnosed. But thanks to breakthrough AI technology, medical decisions can be made in just 5 seconds based on pathology reports. These decisions include drug selection and new lung cancer clinical trial screening that aim to improve survival rates. The interdisciplinary research team at Taipei Medical University are pioneers in NLP and generative AI technology. We employ multimodal prediction methods in order to provide optimal drug combinations and relevant clinical trials in only 5 seconds. By doing so, this reduces the treatment waiting time and can bring major breakthroughs for late-stage lung cancer treatment. We use state-of-the-art NLP models like BERT and generative GPT technologies that are trained on over 20,000 lung cancer pathology reports. Our developed model can quickly extract up to 52 important features and achieve an F1 score performance of nearly 90% in a 4,000 data point cross-validation. This leads current international benchmarks. These extracted features serve as GPT prompts to generate high-quality summaries. The summaries make crucial information easy to understand while ensuring the safety and privacy of sensitive medical data. This forward-looking technology is awaiting US and Taiwan patents. Moreover, our method further links treatment efficacy to survival data from over 5,000 lung cancer patients and uses generative GPT technology to generate the most effective drug treatment options for the best prognosis. This result is like consulting dozens of experts who have read thousands of pathology reports. The method streamlines shared decision-making between doctors and patients. For late-stage lung cancer patients, it will also create the option of using new drugs in clinical trials. Our NLP model can automatically and accurately match global trials for new drugs. Put more simply, once the pathology reports are out, our BERT GPT algorithm not only offers prognosis and medication options, but also matches relevant global clinical trials, which will enable rapid shared decision-making and expanding treatment possibilities. This product is currently undergoing clinical trial with National Taiwan University Hospital. In addition to awaiting approval for 4 patents from both the United States and Taiwan, the technology will be commercialized through the company DeepRad AI in order to speed up its market application and reach. Taipei Medical University is collaborating with the National Science Council to use the latest in generative AI and NLP technologies, along with big data in healthcare, to achieve more personalized and precise treatment for late-stage lung cancer patients.
Okay, so this is the architecture of the method. Okay, so firstly, the patient just need to input the pathology report, and our model, our NLP model, will extract the feature of the pathology report. Okay, and as you can see here, once the patient has been extract the features, so one patient can be represented using the features, and then we can use based on the feature, and we develop an algorithm called PathScan. And the PathScan can help us to search out the similar patient in our patient data bank. Okay, and the result can provide the reference to the doctor, and the similar method can be adapted for the clinical trial matching. Okay, all right. So based on our this year's publications, we adapt multiple large language model to investigate the performance of the feature extraction from the pathology report. Okay, so here we use the tenfold cross validation, and the data is from the Taipei Medical University, and there are about 3,000 pathology reports from 700 patients, and we also do the external validation, and we use the TMU hospital data set, and the data contain about 1,200 report. Okay, and the performance is very good, and the performance can comparable to the human expert. Okay, and for the generalization ability, the large language model is better than the small language model called BERT. Okay, BERT-based model. Okay, so it's very you have the potential that can be adapted in the clinical environment. Okay, all right. So the second case I would like to show you is the NLP in the emergency department. Okay, so here is the process of the ED. For example, firstly, the patient arrived the hospital, and the first is to register and triage. And so based on the process, we want to develop an AI model that can facilitate the process and help the doctor can do the decision making. Okay, here I also prepare a short video for you. So let me play the video.
Taipei Medical University is working with the Shuangho Hospital emergency team to use generative AI to build an intelligent emergency care support system called AIDE. This AI system will boost emergency care efficiency. Emergency overcrowding has become an increasing global medical crisis. Worldwide emergency departments are facing the dual challenge of staff shortages and increasing numbers of patients. More than 60% of emergency departments are overcrowded. In the United States, 43% of people have utilized emergency services. And in Taiwan, 1 out of every 2 people has visited an emergency department. In Canada, more than 25% of patients had waited over 4 hours in the emergency department. Patients who wait too long in the emergency department face an increasing risk of death. Also, medical staff are resigning in large numbers due to excessive overtime work. The global shortage of emergency doctors has reached 30%. In Taiwan, the shortage of medical staff has reached up to 45%. By 2030, the worldwide shortage of medical staff is expected to exceed 2.5 million. Emergency overcrowding not only prolongs patient waiting time, but also drives up medical costs. Facing severe staffing shortages, existing ER systems struggle to identify potentially critical patients and to allocate limited medical resources efficiently. This leads to soaring healthcare spending. A cross-disciplinary team at Taipei Medical University has integrated large language models with generative AI to develop an intelligent emergency care support system called AIDE, which is trained on nearly 300,000 real medical records. And within minutes of a patient's arrival, AIDE can instantly capture vital signs and chief complaints, predict clinical risks and resource needs accordingly, assist doctors in prioritizing high-risk cases, and start the admission process earlier. AIDE can greatly improve resource utilization. Equipped with explainable AI, AIDE provides doctors with more information and reduce the burden of paperwork, effectively addresses the issues of efficiency and staffing shortages in emergency departments, and bring breakthroughs in decision-making and resource allocation. Our CNTR technology, integrated with large language models, is specially designed for emergency care data to enhance the model's ability to comprehend complex text significantly. and through special mechanisms, it can help overcome the challenge of recognizing rare, high-risk cases. It is also suitable for healthcare institutions in multilingual societies. Backed by patents in both the United States and Taiwan, AIDE has been trained on nearly 200,000 clinical records, and in cross-validation tests, AIDE has achieved an overall accuracy of nearly 90%. It has also been successfully validated at Shin Kong Hospital. Using AIDE for decision support can reduce waiting time by as much as 76 minutes, lower hospital costs by up to 6.22 million USD per hospital, and cut CT scans by 50% annually, saving a total of 6.3 billion USD in expenses. Taipei Medical.
All right, so the time is limited, so I need to move to the next slide. All right, so this is the idea of the AIDE. So the model, NLP model here, many model here. So the input data is the vital sign, okay, and the chief component. Okay, so chief component is the text data, and the vital sign is maybe the web data. All right. So here we have multiple NLP model to predict many tasks. All right. So the challenge of the model is to integrate the vital sign and the clinical narrative. All right. So the clinical narrative, as you can see here, is a mixed language and contain multiple simple signals. Okay, simple. And actually the data is very imbalanced. For example, if we want to predict the outcome of the patient, whether the patient will go into the ICU within 72 hours, only 3% patient, less than 3% patient is this emergency case. Okay, so the data is very imbalanced. So maybe you can use the traditional technology to deal with this imbalanced issue. Maybe the resampling, such as the SMOT or the class weight, or maybe you can focus on the loss function, or sometimes you can use the focal loss. But in this research, we start to use the large language model to generate the synthetic data. All right. All right. So the following slides is about what we done. Yeah. So I need to mention that in the first paper, we developed a representation method we called CNTR. So the representation method can solve the mixed language and the short content problem. Okay, and yeah, so you can see the performance is really good. Okay, can achieve about 90% AURC. Okay, so what's our next step? Our next step is to discuss the decision making, the behavior. Whether if we provide the result of the AI model to the doctor, how many doctors will change their decision making? So we want to investigate the decision making, the behavior. Okay, so this is what we want to do in the near future. All right, because the time will be ties up. So the last case I would like to share is NLP in nursing. Okay, so the input data here is the nursing report. In Taiwan, the nursing report content is based on is written by the Mandarin Chinese. Okay, so for this task, we need to develop the Chinese-based language model. Okay, so for this task, actually there is two tasks. The first is ICU delirium, and the second is mortality risk after hospital discharge. So for both tasks, we fuse many features. For example, the vital sign or the mental scale, as well as the clinical knowledge. Okay, so the clinical knowledge is from the discussion between the nurse in our hospital. Okay, So the clinical knowledge is about time information. Okay. So we encode the time information into the language model. And based on our results, if we encode the new feature into the language model, the new feature is clinical knowledge, that can outperform the comparison significantly. Okay. All right. So this is our model architecture. So in this task, we also solve the length limitation of the BERT model. So we develop an algorithm that can filter out noise from the nursing report. So that means we can summarize a shortened nursing report and fit into the BERT model. And finally, the model performance can perform better than previous. Okay. All right. So let me conclude this talk. So in this talk, I share some applications. The first is about the NLP for the lung cancer treatment. The second is for the emergency department. The last is the nursing. Okay. So for all of the applications, our model is the large language model. Actually, it's small language model. Okay, so in the near future, the smaller or faster and the more specific the model is the trend we wanted to do. Okay, thank you. Oh, by the way, sorry, there is a slide I wanted to share to you. We establish a special issue on the BNJ healthcare informatics. So if you have interest in, you can submit your work to our special issue. Okay, thank you very much.
Hi, can everybody hear me? Can you see my slides on the screen?
Yes.
Okay, so I'll start my presentation then. Hi, I'm Paul Taylor. I'm a professor of health informatics here at the Institute of Health Informatics at University College London. I've been researching or thinking about artificial intelligence for a very long time, for about 40 years. I'm not going to say very much about the early part of that because things really didn't work. And I'm going to focus today on what's been happening since 2012. And what I'm going to talk about is very much complementary to the previous talk, which was about generative AI. And I'm going to talk about a different flavor of AI, which we call discriminative AI. And I'll explain what that means in a second. So I want to start by playing a video. I hope you can hear the sound for this.
Jeff, perhaps a similar question, if you may. What do you think some of this exciting work to come?
Okay, so let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the which is the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists because it's going to be able to get a lot more experience. It might be 10 years, but we've got plenty of radiologists already. I said this at a hospital and it didn't go down too well, but there's going to be thousands of applications of the deep learning chips. Those are the ones you're going to hear about. So there'll be lots of that. And I think something, and we have a lot of data, and deep learning is probably going to make it work better than the existing.
So that, I hope you heard that. So that was Geoffrey Hinton, who last year won the Nobel Prize for his contribution to artificial intelligence. And he's really the pioneer of the application of neural networks and machine learning to artificial intelligence. And what he was saying there in 2016 was that it was absolutely obvious to him, given the progress that had been made by then since about 2012, that there was no need for us to train radiologists anymore, because within 5 to 10 years, AI will be able to do the job of a radiologist. And I want to think about what's happened since 2016 in the application of AI to radiology and try and understand where we are and where we're going. And Jeffrey Hinton was certainly right that the technology is very powerful, but he misjudged, I think, the difficulty of turning that technology into products and the challenges in getting those products out into hospitals and used to analyze real images. What you're seeing on this slide is the trend in the approval by the American Food and Drug Administration for medical devices that incorporate AI. And there are now over 1,000 such devices. And you can see that the number each year is increasing. There's a drop off in the last year because the statistics are published in October. So by the end of the year, I'm sure that the line for 2024 would have exceeded that for 2023. And I suspect very strongly that the line for 2025 is even higher. And what you see is that the lion's share, the vast majority of these devices are aimed at radiology. The next most popular specialty is cardiology. And in fact, almost all of the cardiology AI devices are image processing devices, so similar to radiology. And we're seeing in the UK, and I'm sure globally, we're beginning to see some applications of generative AI used as scribes to take records of patient consultations and to summarize patient consultations. And I think in the next couple of years, we'll see a lot of AI devices seeking approval for those kinds of tasks. But at the moment, the majority of applications of AI in healthcare are in radiology and in imaging. But it's not happened, right? So the prediction that Jeffrey Hinton, that who knows an awful lot more than I do about artificial intelligence, a global expert, godfather of AI, Nobel Prize winner, his prediction was absolutely wrong, right? We still need radiologists. So in the city where I live in London, there are currently vacancies for 23 radiologists. So there are a lot more radiologists needed than we have. It certainly isn't the case that we've managed to replace them. So why is that? I think that's a really important and interesting question to ask about the technology. And I'm going to talk about that for most of the rest of the session. But I want, just before I get into the detail of that, to just think for a minute about what AI is, or what the particular flavor of AI that I'm talking about is. And the way I introduce that to audiences is to try and demystify it, try and make it seem a lot less magical, and perhaps more like sort of just familiar mathematics. So just for a second, I want you to think about an application where you're trying to distinguish between patients who have diabetes and patients who don't have diabetes. And you've maybe got a sample of around 10 or 12 patients. And for each of them, just to simplify things, let's imagine you only know two pieces of information, their percentage body fat and their abdominal circumference. Well, if you know two things about them, you can arrange your data in a two-dimensional plot. And then if you want to distinguish between the yellow dots and the blue dots, you can imagine perhaps with a ruler trying to find the line that gives you the best separation between the blue dots and the yellow dots. You're not going to get a perfect separation, but you could find a line that gives you a reasonably good separation. And what you're doing when you're doing that is you're using the data that you have to estimate the parameters of a function that give you the separation. You may not think of it mathematically in that sense, but that's what you're doing. You've got two parameters. You've got how high up the y-axis your ruler is, and you've got the gradient, the steepness of the line. And those two parameters you can estimate from the data by finding values for the parameters that minimize some measure of loss, right? Some measure of error. And that's all machine learning is. It's using the data to estimate the values of the parameters of a function that minimize some measure of error. That's what we're doing all the time when we're doing generative AI. Discriminative AI. Any application of AI these days is almost certainly based on what we call neural networks. And an artificial neuron can be thought of as a very, very simple tool for finding a simple classification. So you have your inputs, those are your parameter values. You multiply each of those by a weight, and the weights are essentially the parameters that the network learns. And then you add them together, you apply some kind of function to make a decision as to whether your output is yes or no, 1 or 0. And this is a very efficient way of learning a simple classification. When I say simple, I essentially mean a straight line classification like we had in the previous example. But the great thing about these artificial neurons is that you can combine simple classifiers in a network to obtain a complex classifier, right? So when I started working in artificial intelligence, I went to lots of conferences where people were giving lots of presentations where they were using neural networks with maybe 20 inputs and 2 or 3 layers, and they achieved a classification which was better than random, but not good enough to be useful. And people kind of gave up on using neural networks really in sort of 1990s because it wasn't really getting anywhere in terms of meaningful tasks, except a very small number of people. And Geoff Hinton was absolutely central for that. And that's why he's such an important figure today, because they found in 2012 that there are actually 3 changes that happened in the world which made it possible to use neural networks for real world tasks. And the most important of those were the availability of much more powerful computers. And actually, the way they achieved that was using the specialized chips from gaming consoles, what are called graphical processing units, the chips that NVIDIA makes that you'll be reading about, GPUs. And the other change was the availability of large quantities of data. So the internet and tools like Google Image Search made it possible to compile very, very large collections of data. And that was important for training artificial neural networks. The third change, which I'm going to talk about very, very briefly, was a technical improvement. And that maybe wasn't as important as the others, but I think it's quite interesting. And to explain it, I need to get you to think about images in a different way to the way you normally think about images. So conventionally, when we talk about a digital image, we think of it as a set of pixels, a set of points, each of which is represented by a number, which is a value between 0 and 255, say, which represents how gray that point in the image should be. But somewhat surprisingly, there's another way of thinking about an image, which is you can think of it as being a superposition of standard patterns. So on the left of this slide, I've shown 64 standard patterns, an array of 8 by 8. I've shown them side by side, but I want you to imagine each of them place one on top of the other. And if you do that and you adjust each of the patterns by a weight, which reflects the extent, the strength of which that's present at that point in the image, then you can create any arbitrary pattern. So you can get something that corresponds to any region of an image. And that's how convolutional neural networks work, which are the imaging, the version of neural networks which has been able to achieve such success in the analysis of image. One of the parameters that they learn is the tuning of these different standard patterns. And I think it's interesting to think about the analysis of images in that way as being identifying the presence within the image of these different component patterns. So that's the background of discriminative AI and a little bit of an introduction to the technology. I'm now going to talk about how it's being applied in imaging. And really the focus here is a particular use case within medicine, which is screening. I think screening is the obvious first case to apply AI. It's the simplest environment in which to make it work for a variety of reasons. Most important of which, it's a really simple decision. It's a binary decision. Recall the patient for further investigations or don't recall the patient for further investigations. And that simplicity of makes it easy to model the decision in a mathematical way and solve it with an algorithm. It's also a decision which is constrained. You're not really interested in the patient's family, the complexities of their history or their social circumstances, or lots of other things which might affect a decision in healthcare otherwise. It's really just about what's detectable on this image. And that's something that you can do much more easily with AI than other tasks in medicine. But within screening, there's different ways you can make it work and different ways in which you can involve the AI. And I've listed 4 here. One is in this country, in my country, and I think in others around the world, when you screen for breast cancer using mammograms or breast x-rays, in order to minimize the error, and the human process is error prone because this is a complicated interpreted task. The images are difficult to understand, and they're noisy and not entirely reliable. Each image is looked at by two trained film readers, two radiologists or a trained radiographer. And so one way of involving AI in the process is to replace one of the humans. Another way you can involve AI in the process is to say that you're not going to automate the whole process, but you're just going to use AI to identify a subset of images which are so obviously normal that they don't need to be interpreted by a human. So you're going to say, we don't think AI can do the whole job, but we think AI can do part of it. And so we're going to say, let's say there are 1,000 images, maybe there are 200 there that are just barn door, really obviously normal, and the AI can classify those as normal, and then those don't need to be read by a human. So that gives us a little bit of saving. The more ambitious thing, of course, is to completely replace the human. You say, we're just going to do what Geoffrey Hinton thought we would do and take the human out and put a machine there in their place. The final thing, which I think is possibly the hardest to make work in practice, is the one that perhaps is most acceptable to the profession and safest from the point of view of the regulators, and that's to help the clinician make the decisions. The difficulty there is that it's difficult to have a body of evidence about how effective this is, because the behavior of the human using the machine is quite susceptible to different contextual environmental features. I can say a bit more about that later. So just as a way of looking at the narrative around this, I've picked a company. I picked Kieran because it's a UK-based company, and it's by coincidence it was launched in 2016, the same year that Geoffrey Hinton was making the comments that I found in that video, that there is no longer necessary to train radiologists. So they were, in a sense, sharing that vision and trying to bring technology to market which would achieve the goal that he'd anticipated we would try and solve within 5 to 10 years. And actually, if you look at their history, they seem to do quite well in the early days, in that they produced a product which they call MIA, M-I-A, and they were able to get that approved by the regulators to be sold as a medical device within 2 years, which is pretty impressive, actually, because they have to create the device, they have to get the data, they have to train the AI, they have to build the interface, they have to do all the software engineering, and they then have to get demonstration as evidence of its effectiveness and its safety so that it can be marketed. And they did all of that within 2 years. It took them a further 3 years to publish a study that showed that the system was safe and cost effective, right? So the information they provided the regulator with in 2018 is private. I don't know what that was. No one knows what that was. But then they published a public trial in 2021. However, in 2022, the UK's National Screening Committee said that kind of trial, a retrospective trial using archived data, is not good enough, right? We're not going to, I mean, it's been approved by the regulators, but we, the profession, aren't going to adopt it until better evidence is obtained. The company then did obtain better evidence, but not with the system being used the way it would be used in the UK. They showed its use as a third reader. So you've got 2 humans and now you're adding a computer, and that does better, but obviously it's more expensive. So we don't want that. And it wasn't until in 2024, the screening committee again said, actually, we think we need more evidence. We need more trials. We need more research before we're prepared to adopt it. And in 2024, essentially the company ran out of money. Okay. So they existed for 8 years. They've been working on the technology all that time, and they had demonstrated to the satisfaction of the regulators that it was safe, but they hadn't produced enough published clinical evidence in terms of trials to convince the profession that they wanted to adopt it. And you can see here a news story from earlier this year from a UK newspaper saying that we're going to do more research, right? So we're still in a position where the profession is saying, actually, we need to do more research before we can adopt this. And I just thought, just to explain a little bit about the way the system works. So in the UK, as I said, in breast cancer screening, each mammogram, each of the breast X-rays is looked at by two readers. So on the left, you've got reader 1 and reader 2. And if they agree, then the woman is either recalled or not recalled. And if they disagree, then an additional reader is involved in the process. And what they Mia have tried to evaluate is the cost effectiveness of a model where you simply replace one of the two readers with a machine, right? So you replace one of the two readers with a machine. And that's a good model to go for two reasons. One is that it's kind of acceptable to the people that there are still humans in the loop. You're not completely handing over things to the machine, which people worry about. And the other is that actually the legislation in the UK that governs the use of X-rays, of ionizing radiation, requires that all such exams are interpreted by a radiologist. Okay, so it's not so the legal framework hasn't been changed to allow us to use AI completely. But I thought this was really interesting to give you a sense of where we are in this particular use case. And this was a cost effectiveness study that was published a couple of years ago. And I think it's really interesting to look at the difference in cost between the machine and the human. So the human costs £5.90 per film, right? The machine costs £4.72. So the machine is clearly cheaper, but it's not free, right? It's not the difference that you might be expecting, because the companies, they've spent an enormous amount of money developing that technology, and the investors want to recoup that investment. So there's a sort of sometimes an assumption, I think, that if we could do this all by machines, we could do it for free pretty much, but that's really not the case. And the thing to think about, to put this into context, is that the cost of reading a mammogram is really cheap, right? If you're thinking about the cost, the healthcare costs in this country, £5.90 is not a huge amount of money. And the reason that it's relatively cheap is that radiologists do it incredibly quickly. So it takes seconds for a trained radiologist to determine whether a mammogram has got cancer or signs of cancer or not. But if the woman is determined to be at risk of cancer and has to be recalled for further investigations, those further investigations don't take seconds. They don't take minutes. They take an hour or so, because you've got to do further mammograms. You've got to take a patient history. You've got to do ultrasound. You've got to do a fine needle biopsy. You've got to do pathology. There's a whole panoply of tests that have to be done with every patient who's recalled from screening. So if introducing AI into the process makes an even fractional change to the proportion of women who are recalled for further investigations, the economics blows up, right? And that's the thing that the professions are worried about. That's why they want more evidence of what's it like when it's used in practice. Because if it changes the proportion of women being screened who are recalled for further investigations from 10% to 11%, it's a tiny change, but it's a huge additional cost. And that additional cost will dwarf the savings that you can make by using AI for the primary step of screening. I think that's a really important point. So I want to just say a little bit about two other applications for medical imaging in screening. And the first of those is diabetic retinopathy. So for those of you who aren't aware, patients with diabetes are at risk of changes in the eye, which if not treated would lead to potentially to blindness. And so they're invited to come for screening once a year. And the screening test is essentially a photograph of the back of the retina, a straightforward fundus photograph. And you can see there an image of the retina with signs of diabetes. So they're testing the fire alarm in my building. So you may hear some noise that's finished now. And it's a interestingly different application to mammography screening for a number of reasons. One of which is that the humans who read these scans are not medically qualified, so that it requires a certain amount of training, but they're a bit cheaper than radiologists. And also the risks are slightly different, because it's with breast cancer, you screen once every 3 years, and if you miss a cancer, it could be really, really serious for that woman. With diabetic retinopathy, the risk equation is slightly different because patients come every year and the disease is a slightly uncertain progression. So you're not quite so worried about missing one case. So I was involved in a research project to look at incorporating AI into the screening process. And the particular model that we looked at was what we've called triage, where the AI would identify a subset of the cases as being so obviously normal that they didn't need to be interpreted by a human. But the majority of the cases that were handled by the algorithm would be still reviewed by a human. So you can look at the two diagrams here, slightly complicated workflow. So in the traditional one, you have a level 1 grader who looked at all of the images, and if they said it was normal, they would just go to annual rescreen. If they weren't sure, it could go to a level 2 grader. But if they were certain that it was abnormal, it would go straight to the hospitalized service. And then you had a level 2 grader who would look at the decisions and see what they thought. And sometimes if they disagreed with the level 1 grader, that could go to a level 3 grader. The level 2 grader would also look at a proportion of the ones that the level 1 grader said were normal, in order just to do sort of quality assurance. And the aim of the automated system here was that it would replace the level 1 grader. So it would identify a proportion of the images and those would go straight to the annual rescreen, but the majority of images would end up being channeled through the level 2 grader. And this is what you see here for the different images that we looked at, and each of the rows corresponds to a retinopathy grade, with the more serious disease being at the bottom and the less serious disease being at the top. And what we're interested in is the proportion of images which the algorithm identifies as having no disease. So IART identified the R0, M0 as being no disease in 20% of cases, and the RET marker identified it as no disease in 53% of cases. So that's the saving, right? That's the images which are not going to be looked at by a human being. The algorithm is saving us money on those. And the other thing you need to look at is the cases further down in the no disease column, because those are images where there is disease and the algorithm has inappropriately said that there's no disease. So those would be errors. And you see the numbers are small, but they're not zero. So we've got 2% of cases have serious eye-threatening disease, and the algorithm has said that they're okay. And we felt, given that there's human error in the process anyway, and given that these would almost certainly be detected within a year or no more than a year, that you could argue that was acceptable, given that you were making a significant saving with the 53% of cases. But it's a difficult argument to make, and the screening committee were unsure about it. And you'll see here that the company was founded in 2010. It took 5 years to get CE marks, so to get regulatory approval. We did the work that I've talked to you in 2016. We did a further trial in 2020, but in 2021. The screening committee was still saying, actually, we're not sure. We need more evidence. And so you see there's real conservatism amongst the profession about whether or not AI is safe to adopt. And to some extent, I sympathize with them, because it does make mistakes. There will be people whose cancers or whose diabetic retinopathy is missed. But mistakes happen all the time. Humans make mistakes. The question is whether the algorithm is good enough that we can build it into a system that's effective and acceptable. And the last example I want to talk about is one where you completely replace the human decision maker. And this is an example from work that we did with Moorfields Eye Hospital, which is a specialist eye hospital attached to UCL. And with the involvement of a company that may be familiar to you called DeepMind, which is now owned by a company that will be familiar to you called Google. And they were interested in applying AI to the interpretation of a category of image called OCT scans. OCT stands for optical coherence tomography. And these are, again, images of the eye. They're three-dimensional images. They look a bit like ultrasound, but they build up a 3D image of the surface of the retina. And what you see in this image is in one column you see examples of OCT scans. In the next column you see human experts who have segmented the OCT scan, so identified the different tissue types that are visible in the scan. And in the third image column you see the AI's attempt to replicate this. And you can see that in this particular case, obviously this is the case that they selected to be in the paper, so it's going to be a good one. The segmentation is incredibly accurate. And then if you look at the performance of this algorithm in a clinical decision, so making a decision about whether or not a patient with this OCT scan needs to be referred. And this is a bit of a pinch point in ophthalmology at the moment, because OCT scanners have become relatively cheap and relatively pervasive. So in the UK, if you go for a routine eye test to see if you need a new pair of glasses, they will offer you an OCT scan to check whether you have got any one of a number of sight-threatening conditions. And there is a condition called age-related macular degeneration, which is incredibly common in the older population. And obviously, in our country, the proportion of the population that is older is increasing. So we live in a country with a declining birth rate and extending longevity. So a higher proportion of our patients are in that older category. And this is an ROC curve. So you've got the false alarm rate plotted on the x-axis and the hit rate plotted on the y-axis. So where you want to be is in the top left-hand corner, where you're achieving 0 false alarm and 100% hit rate. And you can see that the algorithm, which is the blue line, is getting very, very close to that top left-hand corner. And I've sort of zoomed in on the bit that's shown on the left-hand panel in yellow. You can see it zoomed in on the right-hand panel. And you see there the algorithm is compared to the human experts. And for each human expert, we've given them 2 dots. 1 dot shows how they perform with just the information available to the algorithm, i.e. just the image. And the other dot shows how they perform with the additional clinical context, right? So a human making this decision generally wouldn't just look at the image. They look at the patient's history and their age and various other bits of information as well. That information is not, the algorithm can't take advantage of that. So you might say, well, it's not fair to compare the human with that information with the algorithm that can't take advantage of it. But on the other hand, you want the human to see how well the algorithm does it compared to the human doing as well as the human possibly can. So we looked at both points. But you can see that the algorithm basically does pretty much better than pretty much all of the experts pretty much all of the time, right? It does incredibly well. And this was published as a research paper in 2018. Huge kind of fanfare was on the news. It was in the mainstream media. After that, the project was transferred to Google Health, a division of Google. Further research was published in 2020 showing that not only could they classify things correctly, they could do prognosis, so they could predict clinical outcomes in the future. However, in 2021, Google changed their focus and they decided that these kinds of health projects weren't part of their business portfolio. They weren't the kind of thing they wanted to do. Google's health is really focused on things like wearable apps, and technology that can be sold to the general public and stuff that fits with the kind of the portfolio of Google products. Whereas this particular application, which is quite specialist healthcare within the sort of ophthalmology industry, if you like, wasn't part of their portfolio. So the project was abandoned. And since then, Moorfields have taken the intellectual property and they've engaged with a different partner, and a product will come out, but nothing has come out yet. So you'll see that the journey from demonstrating that the technology works to actually having a marketable product that's used in industry, that's used on the front line, handling real patients. It's a difficult journey, and in this case, it hasn't actually completed. So that's I guess most of what I want to say about the history, about what's happened so far and where we are now. And I wanted just in closing to give you something to think about what AI and technology means for the future of healthcare. I've wanted to show that it's problematic in terms of getting adopted, but I think it is going to get adopted. It would just take longer than people thought, and maybe it'll be patchy, and maybe it'll happen faster in some places than other, but it will be adopted. I thought this was quite an interesting piece of reflection from this group in the UK, the Health Foundation, about what are the likely implications of AI for the future of healthcare. And they talked about different ways that you can automate. And I thought this was really interesting. And they divided it into 4 quadrants based on whether the machines are better than the humans or not, and whether the machines help the humans or replace the humans. So in the top left quadrant, you've got machines are helping the humans, even though that the machines are better than the humans. And that's something like using augmented reality to improve the performance of surgeons. And on the top right, you've got a quadrant where the machines are better than the humans and replace the humans. So that's doing mechanical tasks like counting the pills in a dispensing thing. So you completely automate the process. And then in the lower quadrant, you've got cases where maybe the AI isn't as good as humans, but it's sort of good enough. And then it can be used perhaps to substitute for the humans in tasks that aren't safety critical, like using robots to transport samples around the hospital, or taking notes and summarizing consultations. And I think we haven't really talked about that. It's not a focus for me because it's the application of generative rather than discriminative AI. But I've noticed that certainly in the UK, that is the area where AI is being adopted fastest, is that it's being used by GPs and hospital doctors to record patient consultations. And then they use a large language model to summarize the consultation and upload the summary to the record. And it saves them a huge amount of administrative time. But there's a real question about whether or not this can be considered as purely administrative, or whether this is safety critical, and whether these things need to be regulated as medical devices. And I think that's an interesting question. So you can see that there are different ways that you might, different examples of this in clinical decision support, where you have AI used to generate simple reminders and prompts to radiologists or to other doctors. You get that a lot in electronic patient records, particularly around prescribing alerts, to make sure people aren't making common errors in prescribing. And that can be difficult to make work because it's very hard to make the alerts sufficiently specific to be useful. Or you can get much more effective, intelligent decision support of the kind I've talked about with the use of discriminative AI in imaging. And just my last slide, I think this is just thinking about how automation will change radiology, the clinical specialty I've been talking about most. And I think you will see the radiologists won't be replaced, but there will be tasks that have up to now been performed by radiologists that will be replaced. And those will be things like risk assessment, particular detection of particular kinds of cancer, and measurements of image quality. But there will still be lots of elements of the job, like the interaction with the other physicians or with the patient, which will be remain the human part of radiology. And one thing that I think people are looking at is the idea that radiology will change and evolve to being a much more interventional specialty. I think I've used my time, so I'll stop there.
Yeah, thank you very much, Professor Taylor, for such a comprehensive and enlightening presentations. So now we'll move forward into about 30 minutes discussion and question and answer. I think some of the participants actually already posed the questions, but I would like to give a chance also to invite you directly if you would like to raise your questions directly to our speakers. We will open your mic. Please raise your hand if you would like to elaborate more to ask directly to our speakers. Bu Galih, would you like to raise the questions directly? Yeah, otherwise we will start with the questions from the chats. The first is from Bu Galih, which is asking to Professor Chang about many clinicians still feel uncertain about using AI in their daily practice. From your experience, how can LLM be introduced in a way that feels supportive rather than intimidating for healthcare professionals? Yeah, I think you have actually responded also, Professor Chang, but if you would like to elaborate more, so then the other audience may also receive the answer.
Yeah, I think I have already replied the question. So maybe I can emphasize again the large language model is only for the assistant. So if we adapt the AI or large language model into the clinical environment, the doctor still is the most important role in the clinical. Yeah, for example, if making the final decision, I think it should be the decision should be made by the doctor. The AI or large language model only provide the relevant information for the doctor. Yeah.
Okay. So yeah, hopefully Bu Galih already satisfied with the answer, but otherwise we open also the possibility if you would like to raise more questions. But yeah, let's to the next questions from Porwa to Professor Changs. What infrastructure is required to successfully deploy LLM in real-world healthcare facilities, considering that the associated costs are likely to be substantial? And in addition, it is feasible for smaller hospitals with limited resources to adopt such a kind of system.
Yeah. So based on my reply, so in my opinion, I think because the clinical data have many privacy issues, so we cannot use the online large language model such as the ChatGPT or Google Gemini. Yeah. So as I mentioned in my talk, it's the right time we can start to use the small language model, because when we use the small language model, we can develop an AI model in the isolated environment. Yeah, because it's by the way, it's also a small language model. That means we can use only 1 or 2 GPU to run the language model. Yeah, that is my response.
Yeah. Okay. So
if I can just add,
please.
The performance of the small language models is I think one of the things that's changed a lot in the last few years, and they've become a lot more powerful. So that's definitely an option. But I'm intrigued by the adoption in the UK, and I'm sure internationally, of these AI scribes. So these are tools, sometimes it's called ambient voice technology. So these are tools which listen to the consultation and then generate a transcript of it, and then summarize the transcript, and then use that to perform some kind of automated task, like presenting a report to the clinician that can then be incorporated into the record. Because my understanding is that these tools are built on large language models. So it may be difficult for Professor Chang or for me to negotiate with a company like OpenAI an arrangement whereby we can be certain that the information processed by OpenAI respects patient confidentiality. But there are companies out there that are doing that, and they are building products based on that. And the question is whether those are transparent and whether or not they're safe. And what's happened in this country is that the authorities have decided that those products need to be regulated as medical devices, but as class 1 medical devices, which is a relatively not particularly onerous level of regulation. But if you think about it, if you're generating a summary of a patient's record, why wouldn't you check that the actions proposed in that summary comply with the clinical evidence or clinical guidelines or what else you know about the patients? So I think these applications, which at the moment being marketed as purely administrative and ways of saving time, will become kind of decision support tools and actually incorporated into much more into clinical decision making.
Yeah.
Thank you for the comment. I also wanted to point out one issue is about hallucination of the large language model. Yeah, because it's the most important issue if we adapt the large language model into the clinical environment. Yeah, because since it's very important, so my expectation in the future, we should propose a good solution to deal with the hallucination. For example, the RAG technique. Yeah, the RAG technique can fetch the knowledge from or the information from we prepare data set or we prepared knowledge base. So in this way, we can impact the hallucination of the language model. Yeah.
Okay. Yeah. The next question I think will be relevant to both of you. So from Vidya, how can AI improve early disease detections and diagnosis? Yeah, Professor Taylor, could you please respond?
Well, it can improve early detection and diagnosis by doing screening better than humans can, I think. And I think one of the things which I didn't talk about, which I do think is interesting, is what's called overdiagnosis. It's not the same as misdiagnosis. Misdiagnosis is when an algorithm makes a mistake or a human makes a mistake. Overdiagnosis is when you are correctly identified as having a disease that you do have, but you derive no benefit from that diagnosis. So if we screen for cancer, we will detect more cancers than if we didn't screen. And those additional cancers are essentially people who, had they not been detected as having cancer, they would never have known that they had cancer, perhaps because the cancer was very slow growing. So prostate cancer famously is a very indolent, very slow growing cancer. So if you screen for it, you detect more cancers than you need to. And my concern is that AI and imaging will both improve in their sensitivity. And we may find that it's difficult to get the balance right between the level of disease that we are called upon to treat and the level of disease that we can live with. And I think that will be quite a difficult threshold to maintain, particularly it will have issues for health inequalities. If you get people who are consuming more of the healthcare resource than others, and maybe it's actually not for their benefit that maybe they're being kind of over-treated, as it were. But it will take resource away from other parts of the sector. So I think that's a real concern.
Professor Zhang?
Yeah, I agreed the Professor Tyler's response. Yeah, and yeah, I noticed a new question. It's about the privacy data. Yeah. May I answer this question?
Yes, please. Yeah.
Yeah. In my hospital, actually in the data center, we firstly will de-identify the data, especially about the text data. Yeah, and then firstly is the identification, and then the second, if we want to use the identification, the data into the AI, that will relate it to the explanation, model explanation. So sometimes we will use the visualization skill to output the result of the model to deal with the problem of black box. For example, we will use the SHARP or other visualization skill to do it. Yeah.
Yeah, Professor Taylor, if you have additional comment on the questions.
Yeah. So I think privacy is a real problem with when you're using very large data sets. And one of the issues is that you can remove the patient's name and date of birth and address and very obvious identifying information from the record. But what we're increasingly doing with AI is trying to build very, very large data sets with lots of longitudinal data about the patient, maybe the whole of their record from their general practitioner. And if you've got all of that information, then it's relatively easy, if you know a little bit about that patient's medical history, to then access all of that patient's medical history. So, for example, if you have a famous actor or a famous pop star or television personality, and it's in the news that they've had a car accident, then, if people know the day in which somebody was admitted to that hospital, they could search a collection of anonymized patient data and find that individual and find the rest of their information. So we have this legal framework around anonymization, but we also have to have a kind of professional set of practices that have more practical guarantees of preserving privacy, and that involves a lot of technical work. So one thing which we're looking at increasingly is something called federated learning, which is where you're able to run a machine learning algorithm without collecting the data. So the data can sit in the hospital systems where it currently resides, and you can run a machine learning algorithm which is kind of distributed across the hospitals, so that the weights that are learned by the different bits of the algorithm are pooled to create a better system at the center, but the data never actually has to be transferred. So I think that the problem is a real one, and it's certainly one that generates a lot of concern here. And colleagues of mine have ended up in the newspaper with the projects having to be cancelled because it was felt that they were using patient data sort of beyond the boundaries of what had been agreed. But I think that we'll see increasing technical solutions to that. But it is a real problem. Absolutely.
Yeah. So, well, there is another questions from Purwa asking related to when AI is used for clinical decision making, who is responsible for patient safety and outcomes, the developers, hospital, or doctors, and if harm occurs because of AI recommendations, who should be held accountable, especially if AI replaces human decision making?
That's a really difficult question, I think. So the regulators impose standards on the manufacturers, and the manufacturers have to demonstrate that they comply with those standards. So the software has to be developed to a particular framework which guarantees, doesn't guarantee, but it to some level it's a partial guarantee of safety, of good practice. So if they've been negligent, if they've not done everything they should have done, then they could be found fault with. But they could still have done everything they should have done, and the machine could still have made a mistake, right? That's understood. So long as they haven't lied about the performance of the system, or they haven't failed to follow good practice in developing, then that's an error, but it's not a fault, if you see what I mean. And it's just mistakes happen. The clinician, however, if the AI recommends something and the clinician is negligent in not checking it, then the clinician is at fault. Okay. So if the clinician is supposed to check everything through and make sure that any mistakes made by the AI are corrected for, and the clinician hasn't done that, then the clinician is potentially at fault. If the hospital has commissioned a system which hasn't obtained the necessary regulatory approvals, then the hospital could be at fault. So there are different places in the system where people could be found fault if they haven't done what they're supposed to. But it's still going to be the case, I think, that mistakes will be made. The hope is that we make fewer mistakes than we do at the moment. Mistakes are made all the time at the moment. I think one of the interesting questions which occurs in AI, and it's not just in medicine, it also occurs, for example, with safe driving cars. So one argument that's often made with self-driving cars is if the car makes fewer errors than a human, then we should shift to using the AI rather than the human, because that way fewer accidents will happen. But one other argument you could say is, well, actually, maybe we should hold the manufacturers of self-driving cars to a higher standard, because they will only meet the minimum standard that we try and impose on them, right? They'll try and get away with the simplest possible solution. So maybe we should demand more than just being better than the human. And you can make the same argument about AI in healthcare, I think.
So if Professor Chap would like also to elaborate on these questions, please.
Yeah, in my opinion, I think, the responsibility should be shared. So developer ensured the safety and the transparency. So as I mentioned before, for now, the AI must be seen as the support tool. Yeah, so the responsibility is on the doctor. So that means the decision making is by the doctor. Yeah.
Yeah. So, well, another questions I think is related to contextualize the models from Putri, that one big concern in AI for medical imaging is data bias. For example, that most models are trained on dataset from Western countries, which may not reflect populations in other countries like Indonesia. From your experience, how can we mitigate this bias so that AI imaging tools remain accurate and safe across diverse populations?
That's a really, really good question. I think that's a really important issue. So there's a great paper that came out a few years ago looking at dermatology, and it found that the majority of dermatology algorithms were trained on people with white skin, and they perform less well on people with different skin tones. And in ophthalmology, we found that retinal pigmentation varies, and algorithms are affected by retinal pigmentation. So it's absolutely the case that you need to make sure that your algorithms work on the population that you're using them on. And that, I would guess, probably means that you don't want to start from scratch. Probably that the best thing to do is to take an existing algorithm that's been developed for the market that the companies are most interested in, which is going to be North America and Europe. But you want to be able to adjust the algorithm so that its performance is appropriate in the country where you're using it. And so there'll be some what we call fine-tuning that needs to be done. And I think that requires that people build different diverse data sets that reflect the characteristics of different populations. But it's one of the things that's really weird is that algorithms seem to be able to detect ethnicity in images where humans can't see any ethnicity. So a radiologist looking at a chest X-ray has no idea of the ethnic background of the patient. I mean, you just can't, there's nothing in the X-ray that gives you any clue. But you can train an algorithm to distinguish between, this is the work was done in the States, and there's distinguishing between black, white, and Asian populations. Really, really striking that the algorithm was able to do this, and nobody really understands how it does it. It's quite mysterious.
Yeah, Professor Chang, because I know that there are also significant number of migrant workers in Taiwan. So, for example, some stats mentions that 70% of the elderly people living in Taiwan was actually take care of Indonesian people. I just would like also to probably raise the questions whether this issue is also maybe also the same case in your situations, or and any comment on this?
As I mentioned in my talk, one application is NLP for lung cancer treatment. So in that task, we use we not only use the Taipei Medical University data, but also use the National Taiwan University data. So that means we do the external validation. So because the question mentioned the data bias, because many model trained from maybe other countries' data. So firstly, if we adapt the trained model into the Indonesia. So firstly, we need the first step for me need to collect the localized data, okay, and do the external validation. Another way is like the Professor Tyler mentioned, federated learning. So we can use the federated learning to cooperate with other institutes to share the training result of the model without sharing the data. Okay, so under the good mechanism, and we can improve the model performance as well as the model will become more stable. Okay, so that's my answer to the question. By the way, maybe sometimes we can use the open data to do that.
Okay. I think the last question is more for beginners who would like actually to start to understand and also engage with the AI. Since that actually some of our participants is come from the health institutions that train the health professional. For students and clinicians who don't have a technical backgrounds, how can they best engage with AI, imaging research or practice? And what skills should future healthcare professional develop to work effectively?
Yeah, I think maybe I can answer this question first. Yeah, because the question seems like will be asked by my student. Yeah, because in Taipei Medical University, our students don't have the AI background. So yeah, maybe they are doctor or nurse, or they have the clinical background. Okay, so in my opinion, I think in the near future, the student or the healthcare professionals need to have ability. We call it prompt. Yeah, because we should to learn how to interact with the large language model or interact with the AI tool. So nowadays we use the prompt and we can write a prompt to interact with AI model. So in my opinion, in the near future, everyone will become a prompt engineer. Everyone have a expert ability on the prompt engineer. Yeah, that's my answer.
Yeah, thank you. So would you like to say something also, Professor Taylor?
Yeah, so we're actually introducing modules about AI into our undergraduate medical curriculum. And so we've been thinking, what is it that doctors need to know about AI? And I think it's true for different professions as well. I mean, the exact mix will vary. But the doctors, by and large, they're not going to be involved in creating AI products. They don't need to be able to write software. If you think what are the tasks where they're going to engage with AI, so those might be to do with assessing the safety of the AI, right? So they need to have some understanding of the kind of thing it's doing and the kind of errors it might make. They might be involved in commissioning the purchasing of AI products. So they need to understand what they're being told by the vendors, right? They need to have some understanding of the not deep understanding, but broad understanding of kinds of AI that are out there and the kind of products and what their strengths and weaknesses are. They're also involved in interpreting the output of AI. So they have to know what it means and they have to know what the safety metrics are. They have to understand the scores on which the accuracy of the algorithms are assessed. And lastly, they need to be able to explain it, right? They need to be able to talk to their patients about how these decisions are being made and what the role and the place of the algorithm is. So I think there's a lot to learn, but it doesn't but it's not about the sort of the technology. It's not about the equations or being able to write the software. It's about understanding how it works at a level which allows you to do your job. It's almost like, I suppose, like a radiologist and an MRI scanner. I mean, a radiologist at some level needs to know what's going on inside the MRI scanner, but they don't have to have a degree in physics. They don't have to understand it at the level of the really fine detail of how the machines work, but they have to sort of know enough about what's going on to be able to perform as a competent radiologist. And I think it will be the same thing.
Yeah. Thank you. So still one. Oh, it's actually already run out of time. But I have one question which is related to the cost effectiveness requirement. Since Professor Taylor mentions on your presentations about this cost effectiveness, just wondering, since that this is also the things that we in Indonesia usually will consider, and you on your slides this requirements include the setup cost, maintenance, etc. And just wondering, because usually in many cases in our situations they would like actually to have evidence first whether this is will be cost effective or not, but of course in most of cases the evidence is not yet there. And are there any way to basically like predict whether in terms of the cost it will be have beneficial or not? Just for example, like the future economic evaluations that maybe can be predicted, or how you would like to comment on this?
It's really hard. It's really hard. And we found with when we've been working with companies to try and do a cost effectiveness evaluation, the companies haven't wanted to commit to a particular price point. The company will say, why don't you tell us at what point the technology would become cost effective? And then we will work out from that what price we will charge. Because obviously, it's not like it's not like buying something like a loaf of bread where everybody knows how much it costs to make. All of the cost is in the setup and the experiments and the creation of the artifact, and then the amount of revenue you can generate from it is entirely separate, because it doesn't actually cost you anything to do the processing. You just have to find a price point which maximizes the revenue so that you recoup the investment and make a profit. And I think I don't really have an answer. I think it's kind of elastic. But something that's really interesting is if you look at the economics of the sector as a whole, right? Not as an individual manufacturer, but what's going on globally. You will see that billions are being invested in the tech companies. And it's quite hard to see where the money is going to come from to pay that back, particularly when it's not like when there have been previous speculative booms in things like railways, because what their money is being spent on is GPUs, and GPUs last 6 years. So if they've not managed to recoup their investment in that time, then the companies will disappear. I think it's quite hard to see how the economics of the sector work. I think if I was able to answer your question, I'd probably be doing something a lot more lucrative than this.
Yeah. So, since that we already run out of time, so as we close today's session, I would like to sincerely thank our distinguished speakers, Professor Yung-Chun Chang and Professor Paul Taylor, for sharing their valuable insights. So appreciations also to all participants for joining and contribution to our discussions. So before we finish, we would like also to inform you that the next guest lecture will take place on Thursday, 25th of September, with the theme Building Green AI with EHR, Standard Infrastructures and Real-World Data. So really thank you very much, Professor Taylor and Professor Chang, for sharing your expertise, and I think we learned a lot from these sessions, and hopefully then we can still continue doing something and to collaborate also in the next future. So I think we can close this session and see you in the next sessions. Thank you very much.
Thank you, everyone. It was a pleasure.
Thank you.
Thank you. Bye-bye.
Thank you, Professor.